Good morning students, welcome back to digital electronic class. In the previous class we have discussed multiplexer, demultiplexer and the decoder. In today's class we are going to continue the same combination logic circuit. In today's class we are going to continue the concept of encoder. So basically what is the meaning of the encoder? So encoder in the sense we are having 2 power n number of inputs and the output would be n, right? So in this quite a reverse of decoder. In this it is also type of combination logic circuit that depends upon input combination needs to be 2 power n and output combination should be n. So whatever the input is there depends upon that it is going to take the output. So this is your n value. This is what 2 power n to n line encoder, right? So what is the meaning of it? So as you can see here, it has different combination of inputs. Based upon this input combination, it's try to produce the output. So here it is quite similar to your multiplexer, but it's in multiplexer the output is single, but here output is depends upon this n factor. If you do have 4 inputs, so if I'm writing this is my 4 inputs, what about output would be? It's 2 power 2. That means output is 2. If I do have 8 inputs, that I can write as 2 power 3, I'll get the output as 3. That means depend upon the input combination your output is going to be decided. This is nothing but the concept of encoder. So in encoder what is the thing we are going to do it? In encoder we are going to convert 2 power n input combination into n line output combination. That means it is 2 power n into n line encoder. So in this if you do have 4 to 2 line encoder or it can be 8 to 3 line encoder. So based upon the input combination we are going to decide the output factor. So here based upon these things we are going to perform the encoding of the signals, the encoding of the information or encoding of the input bits which we are giving to the encoder. So based upon that we are going to write the output combination of this particular encoder. So in this what is the things we need to do it? Again we need to perform all the things which we have done for the decoder, but in decoder we did the decoding of the sequence, whereas in this we are going to encode the sequence, encode the input bit informations which we are giving to this particular block. So let us see how do we get it this thing. So what we'll do it, first thing we'll take, what is the first example I'm taking 8 to 3 line encoder. So in this what I'm doing, I'm taking 8 input combination. What I'll do it, I'll first write its block. So I do have this particular block. So what I'm doing, 8 to 3 line encoder. So in this what I'm doing, I'm taking 8 inputs. Suppose here 1 2 3 4 5 6 7 and 8, starting from data bit 0, data bit 1 2 3, data bit 4, data bit 5, data bit 6 and data bit 7. These are your 8 inputs. So now what are the outputs values? Suppose this is my output value x, y and z. That means as you can see here, so the inputs values are 8 inputs we just want to write that particular combination. By looking into this particular phenomena we are going to decide what is the output value. So this is your output for encoding the information. This is our what? These are your inputs. So in this what we did students, so we took input values of 8, that is the input bit, the remaining second digit indicates the output bit. So now this thing we need to draw its particular truth table. So first thing we need to draw the block diagram, we did it. Next thing we just want to write the truth table based upon this 8 to 3 line encoder. So that 8 to 3 line encoder we will write the truth table based upon taking the input values from 0 to 7 and the outputs we are mentioning as x, y and z. So based upon these things it is going to consider as the digital circuit that perform inverse operation like decoder. So in that what is the things we are going to do it? We are going to write how do is going to be convert into 8 to 3 line encoding or 8 to 3 line encoder. So that things we are going to write it down. So what is this 8 actually? If I want to say it is 8, I can say it is what? Octal, right? Octal to 3 lines is nothing but 1 will become enable. I left with 2 values. So this 2 is nothing but binary. So I can say octal to binary encoder. So what is another name for this particular encoder is octal to binary encoder. So in this what I'll do it, I'll take the input combinations. What are the input combination I do have? I had input values are starting from all the particular combinations. So we just want to write down all the values. So first is D0, D1, D2, D3, D4, D5, D6, D7. So these are our inputs combination. Next we do have output as X, Y and Z. So these are our truth table. So in that what we did, we took the input values. So these are inputs value D0 to D7. What are the output value? X, Y and Z, right? So what are the inputs value? I just want to activate the D0. That means I need to go for enabling the bit of D0 should be high. So for doing this thing, what I'll do it, first I'll draw it D0 to D7. I did. Next thing, I need to write down the values for respective input bit combination. For that, what I'm doing, I need to generate the output combination value by considering this thing. So what I did, I took from D0 to D7. So now I have D0. D0 bit is high. D0 high means what? This is nothing but mean term M0. So remaining, I don't want to activate or I don't want to go for the combination of all the bits. It's quite same as 3 to 8 line decoder. It is reverse we are doing. So here, so D0 we don't want, we want D1. So D1 should be high, remaining all will be 0. So what is D1 combination? It's nothing but, so if I'm saying 2 power 0, 2 power 1, 2 power 2 like that, it is what? 0, 0, 1. That indicates it's D1. Likewise, I want to go for next combination D2. So to get D2, what I'll do it? D2 means which bit should be there? 2. That means it should be high and this should be low. Clear? Now I just want to go for D3. So how do we write D3? 1, D3 should be high, remaining should be low. For that D3, how do we write? 0, 1, 1, right? 2 plus 1 make it as 3. Likewise, I can go for D4. So D4 would be like this, remaining all 0. So D4 is here 1, remaining 2 will be 0. Likewise, I can go for D5. So D5 bit will be high, these 2 will be low. So D5 means I'll go with 5 plus 1 make it as 4 plus 1 make it as 5. Likewise, I can go for D6. So D6, where is the D6 bit is there? This is D5, this is D6 and this will be 0. So D6 bit will be high. That means 4 plus 2 make it as 6. I can make it as 7 also. So remaining all are zeros except D7 bit. That indicates all is 1. So this is what actually, this is called 8 to 3 line encoder. In other way, I can say that octal. Octal to binary encoder. So binary means 2, but do we had here we had 3. So 1 will behave like enable. So in that we'll consider this 2 and we will take this 8. So this is the way, if they gave an exam to explain 8 to binary encoder or octal to binary encoder, 8 to 3 line encoder, the same thing you need to explain. So first thing we did with the block diagram, next we did with the truth table. So this is how this encoding sequence is going to operate. So this thing we did. Next thing is that how it is going to work as a encoding sequence. So that I'll tell you. First you noted down this particular point for encoding sequence. Next students, we just want to write down the combination of the output. So for writing the combination of the output, what we'll do it? We will write the output value of X, Y and Z. For writing this thing, what we'll do it? We'll take the combination value. So when it is high. So as you can see, X value is high for, what is this value here? D4, D5, D6 and D7. So here see, you can see here for D4 it is high, for D5, D6 and D7. For X I can write D4 plus, D5 plus, D6 plus, D7. This is the X output. Similarly for writing the Y, what I can write for this Y? Y when it is high, this is D0, D1, D2. So see, for D2 it is high, D3 it is high, D6 and D7. So what is the value I can write for this? I can write D2. So this is D2 plus, next value I can say this is nothing but D3. D3 plus D6 plus D7. This is the Y. Now for writing the Z, what is the Z value when it is high? For D1, D3, it's alternate. So we can write D1 plus D3 plus D5 plus D7. So see here, for D1 it is high. When high means 1. When it is 1, column wise you need to look into the particular combination. For that we wrote it, we got the D1 value. Similarly, for the next combination, as you can see, it is D3. For the next combination, you can see it is D5. For the next combination, it is D7. That means this is your output encoding, right? So this combination of that particular thing produces this particular output X, Y and Z. So clear? So this thing we can implement by using OR gate. So X, Y, Z, we will take those particular input combinations. D1 to D7 will take. These are inputs, right? So we'll try to write X value. So how do we do it? So I just want to explain here. The first thing what we did, students, once again you see, first part we need to explain what is an encoder. Encoder is also type of combinational logic circuit which performs encoding of the information of 2 power n inputs to n number of output. What is this n indicates? From the input combination of this n value, it try to get the value of n. So this is your output, we got it. So if you can write that one by taking the example, I can say that I do have 4 to 2 line encoder or 8 to 3 line encoder. 8 to 3 line encoder, one more name is what? Octal to binary encoder. That example we took here, and we'll try to write the encoding sequence. So we wrote the truth table. So respective output also we wrote it as per the given information of the truth table. Next thing, we wrote the combination by taking that particular truth table. Next criteria is that implementation of this thing by using the basic logic gate diagram. So that part we were going to see now. So in this what we'll take all these particular input combination into consideration. So we do have how many inputs? We do have D0 to D7. So this thing we need to write it down. So by taking these all inputs D0 to D7, we'll try to write the output value. So this thing we will do it now. So in that we don't require any kind of NOT gate because there is no bar, right? So only we have to take that D values into consideration and we will draw its logic diagram. So what we are doing, we are just want to write down these things. So we do have D0, then D1, D2, D3, D4, D5, D6 and D7. So these are our inputs value. So we just want to write it down. So in this vertical way, I'm going for vertical approach. So in that, how many OR gate I required? I required 3 OR gates. So first OR gate is here. That is the first OR gate. Next OR gate. And one more OR gate. So what is the first output? I just want to write X. Second output Y. Next output Z. Right? So these are our combinations. So these things we will mention. So we wrote it all these particular value now. 4, 5, 6, 7. So take the connection from 4. This is your 4, 5, D5, 6 and 7. So we got the first output for X. For the output of X encoding sequence we done. Next thing for Y. 2, 3, 6, 7. So we'll take the values from 2. This is your 2. Next is 3. 2, 3, 6 and 7. So right. So we're done with the second output Y. For the next thing, what is there? Z. How do we write? 1, 3, 5, 7. Alternates you need to take. So 1. This is your 1. 3. This is your 3. 1, 3, 5. 5 input combination of it, then 7. So this is the way we got the output. This is OR gate 1, OR gate 2 and OR gate 3. Right? So now we implement by using the basic logic gates for these particular combination. So after that, your complete 8 to 3 line decoding, encoding of the sequence has been done. So these 8 input sequence we encoded into XYZ. In that the combination is here and the gate level designing is over here. So make a note of this thing of 8 to 3 line encoder or octal to binary encoder. This is the way you need to go for this particular approach for designing the encoding sequence. So students, so we did what is the thing we completed in encoder, students. So we start with block diagram of it, the truth table of it, the combination of that particular truth table by taking this function. Next thing we done with the logic diagram. So this is the way we completed the encoder. So until now what we done, we talk about the multiplexer, demultiplexer, encoder, decoder. So these are the parts of our combination. logic circuitry. Next part, we are going to deal with the magnitude comparator. So now how the bits is going to be compared with the next consecutive bit. So bit by bit comparison, that part we are going to see now. So this is about the encoding. So next thing we are going to continue with the magnitude comparator. So students, we are going to come to the magnitude comparator. So in that, what is the first thing we should know? What is the meaning of magnitude? So magnitude comparator. So basically what is a comparator means? So now we are going to magnitude comparator. In that, what is the meaning of comparison? Comparison is nothing but here we are going to compare the first bit. If I do have A bit, if I do have B bit, in bit by bit, what are the comparison is possible? That bit comparison also we are going to do it in digital electronics. So in that, if I am taking the truth table of 2 bit, so what I'll do it? I'll take 2 inputs. What are the 2 bit in combination of the values for it? So 0 0 0 1. 1 0 and 1 1, right? This I can write. So what is this thing I can write? First, whether A is equals to B. This comparison I can do it whether A and B both are same, or A is greater than B, or A is less than B. So out of this, at what particular point, what is the possibility? So for this, first thing, bit by bit comparison I am doing. So either A is equals to B, yes, 0 and 0 are same, so it is high. Similarly, whether A is equals to B, no, because A is 0, B is 1. That means both are different. There is no possibility that they both will be equal. Similarly, here A is 1, B is 0. So A 1, B 0 means they are not equal. Similarly, A is 1 and B is 1. That means A and B are equal. That means it is equals to 1. So we got this is the first comparison of A is equals to B. Similarly, I can write A is greater than B. Whether A is greater than B or not, for that bit by bit. Again compare, 0 is not greater than 0, not possible. Similarly, 0 is greater than 1, no. A should be more than B. So 0 is not greater than 1, again it is 0. Similarly, for the next thing we can write, 1 is greater than 0, yes, it's 1. For the rest of the bit, it will be 0. For the third output, these are what we are doing. We just want to compare the bits. So then we'll write the block diagram, how we'll get it. So the next thing, A is less than B. So just see first bit, 0 is less than 0, no, it is 0. Now next thing, 0 is less than 1, yes, it's 1. 1 is less than 0, no, it will be 0, this will be 0. So what we did, students, so we did comparison of each consecutive bit of the input combination. If you want to perform it, that particular phenomena is considered to be the magnitude comparator. So in the magnitude comparator, what we are going to see the block diagram of it, we will say that for doing the magnitude comparator, in this we are going to take the input value. So if I am having inputs value, suppose A, B, right? What are the outputs I'll get? I'll get 3 outputs. Either A is greater than B, A is less than B, or A is equals to B. So these is our outputs. So in this only we are going to tell the comparison of bit. So between that, possibility is that A can be greater than B, A can be less than B, or A can be equals to B. So if you want to go for these particular assign operators in the digital electronic circuitry, that considered to be the magnitude comparator. So till now what we have done, we have taken 2 bit inputs. In that total combination we got it as 4. We done the first output, second and third. As per these outputs, we need to write its comparison of the bits. So we wrote the block diagram. Next thing is that we need to realize it by using the K-map. So for that, what we'll do it, we'll take the inputs combination. So we will take first input combination is A, B. So 0, 1, again 0, 1. For the second input combination, we can write, again it's two inputs we do have. So it's 2 variable K-map, 0, 1 and 0, 1. For the next, we can write it over here. So we do have 0, 1, 0, 1. This is for A and this is for B. So we wrote it. Next, we need to write the output for first one. When A is equals to B, A equals to B output I want to write. For the second output, I need to write for output A is greater than B. For the next output, I need to write for A is less than B, right? What is A equals to B when it is there? At 0, 0, at 1, 1, right? This and this, I can combine, I can write A complement B complement plus AB. I get this thing. Similarly, for A greater than B, when A greater than B is there, A is 1, B is 0. A is 1, B is 0, this is 1, right? What I can write? A, B bar. Similarly, for the third one, A is 0, B is 1, this is 1. So that is nothing but A bar B, right? So now we need to write the output by taking this truth table, this thing, by considering the particular logic. So what we are doing, we are passing this thing with one NOT gate, we got B complement. This again I am passing with one more NOT gate, I'll get A complement. I need to write the first. So I can directly write this as this thing, or I can write A exclusive NOR. It's similar to an exclusive NOR gate, right? A complement B complement plus AB is nothing but A exclusive NOR with B. So I can mention here exclusive NOR gate. This is for A is equals to B. So I'll take the first combination from A, second combination from B. Next, A B bar. Next I'll take from A and next from B, B bar. So this is our next combination. This is for A is greater than B output. Similarly for third one, A complement B. So A bar B. I can pass with one more AND gate. So A less than B. So this is the way we perform the magnitude comparison of the two bits. It's block diagram, truth table and realization of the function. So this thing we can cover with this particular realization. So it's quite little bit blur it is there. So once again I'm saying students, so see here what we did. We have taken A and B. A, B is there. Then we compare with A is equals to B. Then A greater than B in A less than B. For that we have compare A and B when it is same. So for that 0, 0 it is same. We wrote 1. 1, 1 it is same. We wrote 1. Rest of the thing there is no comparison possibility there. For that's the reason we make this as 0. Next thing A greater than B. For A greater than B when it is there, only for this 1 and 0. A is more than B. For that it is 1, remaining will be 0. Likewise A less than B. It is possibility is over here. So we wrote it 1, remaining is 0. Then the same function we did with by considering this with A equals to B, A greater than B, A less than B. So we got these particular three values. By considering these values we wrote the logical diagram for it. So this is the way you can write the bit by bit comparison of respective combination. So that's how about your unit 2. So unit 2 we just deal with these particular things. So I gave questions of your unit 1 unit 2 importance in your group. So solve those questions. If any query you do have, you can send me the mail of that particular topic. I'll just clarify it, or you can put a message over there. Thank you.